So again, hello everyone. I'd like to welcome you to our monthly virtual technical talk series. And then this is Houston EAGE Houston Local Chapter. We organize this talk like every month, and in that series we are going to hear today from Kathleen in our session. So before we start and into our session, let me remind you that you all are going to be muted in this whole session. But you can use your chat options for communicating with us, as well as you can post your question. Now, the topic of today's presentation is understanding and communicating the geological risk of long-term fate of stored CO2. So it is all about CCUS and then related technology. And this presentation is jointly prepared by Kathleen Gould and Shelagh Baines. And I'd introduce both of them one by one. So let me first go with Kathleen, and she is going to be the speaker of today's talk. And as you can see, Kathleen works with Halliburton Landmark, and she's a geoscience technical consultant and based in Calgary. She has worked as a geologist for over 15 years across petroleum exploration, sustainability, and including mining industry. Shelagh Baines, who has co-authored this presentation, she works for Halliburton Global Consulting. She's a sustainable energy practice lead in Halliburton Consulting. She is based in Denver, and she has over 20 years of experience in carbon storage and development. So in this talk, Kat is going to go through the very high level overview, and then she will share some of her experience while working with some of the technology of Landmark in this particular carbon capture and storage field. So what I'm going to do, I'm going to stop sharing now, and then Kathleen, I'm going to hand over the session to you, and now you can start your presentation.
Okay, I am going to share my screen, and let me know if you don't see a very bright and colorful slide in about 1 second here. Okay, I think that looks
good. I can see your screen, and then once you put it into the full screen mode, then Alan, if you don't mind, just confirm that you are also seeing it perfectly.
Yes, I can see it.
Okay, let's get started.
Okay, thank you very much for your introduction, Kellyanne, and thanks for inviting me, myself and Shelagh Baines, to come speak with you today. Shelagh is actually at the AAPG CCS conference, I believe, this week. So I believe she'll be joining us shortly to help with the Q&A section. So I'm very excited to join you today. I'm excited for the opportunity to be involved in carbon storage modeling as a geoscientist. It kind of reminds me of the passion and interest that I felt when I became a geologist a long time ago. Now, working in frontier kind of spaces, we've got that same collaborative mindset between groups, between industry and government, and it's really exciting. And I hope that after this talk, if this is a new field to you, that you will kind of be similarly invigorated by just learning a little bit more about carbon capture and storage. So we always start every Halliburton presentation off with a safety moment, and this is around fire emergency readiness. So whether you're still working at home or you're back in the office, just ensure that you know where your fire extinguishers are, that they're in good working order, and that they're not expired, and that you know where all your exits are. And folks in your house kind of have a plan if there's a fire, because it's something that we live with every day as humans. So today I'm going to take a kind of a macro view of CCS. We only have 45 minutes to talk about this. So we are going to focus on first talking about CCS or carbon capture and storage. I'm going to use CCS throughout the presentation just to save time. We're going to be focusing on the storage part in the subsurface. Next, we're going to talk about the role of geoscience in effective appraisals for CO2 storage projects. And we're going to focus on kind of the pore scale level, starting to talk talk about the focus of getting the simulation piece right, because that's really going to help us get to the point where we can quickly assess projects and understand dynamic long-term plume modeling. I'm going to touch on a little bit of a demo within our Halliburton landmark software known as Prometheus CO2, just to show folks what it looks like to run one of these simulations in 2D and in 3D. So start off, as we all know, CO2 is a major contributor to the rise in global average temperatures. Reducing CO2 emissions to net zero by 2050 is consistent with our efforts to reduce the global average temperatures to less than 1.5 degrees. And to do this, we really do need everyone to get together and transform how we produce, transport, and consume our energy. In short, net zero by 2050 requires strong action now. And more than ever, companies are overhauling their business models to decarbonize their operations and invest in low carbon assets to meet net zero targets. And in tandem, our legislation, our regulatory frameworks from governments is also being rebuilt to encourage investment in renewable energy and low carbon solutions. So Halliburton is no different in this space, and so I'm just using our kind of overall commitment to energy transition by showing like what we're up to in this space. And this is quite similar to what a lot of companies are doing. First, kind of taking an internal look at how we how we work internally, how sustainable we can be with how we operate on a day-to-day basis, how much we're investing in supporting innovation through Halliburton Labs, which is a way that we help grow new tech and support new tech, how we can offer strong services for geothermal and wind operations, so in the renewable space. And then specifically, we do know that petroleum will continue to play a part in our energy mix as we move through the energy transition. So in order to achieve net zero, we really do need to understand how we're going to manage carbon. What services can we offer as a company to manage carbon, and how as a society are we going to manage the emissions that we continue to produce? So the quote I have up here is around IEA's Sustainable Development Scenario program, saying that we need 260 times the amount of CCS that we have now to prevent 240,000 megatons of CO2 from accumulating in the atmosphere. A little back of the envelope calculation here, that's about 52 billion cars. So that's a lot of cars off the road. And that's just a way for us to understand the impact that CCS is going to have on reducing our overall carbon footprint. And so moving on to talk specifically about CCS, let's take a really high level view. And I really like this image from Enhanced Energy, located up here in Canada. I like it because it humanizes the process of going from carbon capture from multiple sources, petrochemicals, processing, ethanol, direct air capture. How are we going to transport that CO2 to a location where it can either be used, which if you hear the U for CCUS, that's utilization, or what we're going to talk about today, which is long-term permanent storage. And focus long-term CO2 storage. And long-term here, you might ask yourself, what's long-term? 10 years, 50 years, 100 years. Long-term is defined in many different ways, but one of the best definitions I've read of it is a minimum of 1,000 years with a leakage rate of less than 0.1%. So we ask ourselves a variety of questions regarding how we go about storing in the subsurface. How do we permanently store this? And we can store it in a variety of reservoirs, but the two main receptacles that we are focused on are depleted oil and gas reservoirs, so ones that may have some residual hydrocarbons but are no longer economic, and deep saline aquifers. So those are aquifers that are at a particular depth is conducive for storage. They're not drinking water aquifers. And the advantage with the saline aquifer is that they have very, very high potential storage, a lot of pore space. 70% of the 90 announced projects in the US are in deep saline aquifers, and they stand to contribute significant pore space so that we can achieve good permanent CO2 storage. So focus in on North America specifically. If you're like me, I really like web mappers. I like GIS products. I like interlayering things. So go ahead and go over to the DOE map viewer here, the NatCarb viewer, and that's going to help you interlayer some different spatial products around CCS, and you can kind of have a look at that. So that's what we'll use to talk through this today. I want to focus on North America because first, this is a Houston-based talk, but also I believe that North America is well positioned to help with the 2,000 plus large-scale facilities that we need by 2050 to achieve net zero emissions. So according to the Global CCS Institute, that's 100 times more than we have today. So this map shows the outline of the saline aquifers. So we have good saline aquifer coverage. Doesn't mean every one of these is perfect for storage, but we have a lot of them. And then if we do a source to sink kind of geoscience approach here and we sort of overlay our source points, stationary sources, we can focus in on industrial sources specifically, so large point source emitters like our petroleum, our mining, as well as ethanol sources, and we can kind of see that there's good overlap, and that's important for transporting how the costs are of moving CO2 around once you've kind of captured it in the atmosphere. And then I like to look as well as kind of where we're going, what are people investing in right now, and these two maps, commercial facilities and hubs, show in red the locations of ongoing facilities that are currently in operation. So there's a number of them, but they're far outnumbered by the ones that are in development in dark blue here. And similarly for the hub scenarios. So these are large point source emitters that are kind of injecting in pretty near to where they're capturing, whereas the hubs kind of benefit from the economy of scale, aggregating, compressing, and transporting as a group of different suppliers, essentially, to a central point where they can inject. So this kind of just shows you that there's a lot going on in North America, and we stand to contribute quite well to this, the large-scale facilities that we really need to meet those net targets. And moving on to speaking specifically about a carbon storage project, I've purposely chosen not to show sort of a linear, first we do this, then we do this, then we do this, because really a carbon storage project is an integrated operation rather than a linear workflow. These are interconnected pieces with no definitive start or end, and if you remove one of these, you can't really have the project. So I'll just point out here that as geoscientists, we probably typically think of ourselves participating in the technical suitability of a project. How do we define the site? How do we figure out how risky it is? How do we provide information to folks that are going to go ahead and execute? Whereas realistically, the subsurface work program needs to be aligned with all the parts of the CCS framework. We provide information needed for business support to ensure it's commercially successful, that we meet regulatory framework guidelines, that we produce the amount of information that's needed to pass regulatory-wise. I always like to say that geoscientists and engineers, we have a responsibility to communicate to society to ensure that it's clear that what we're doing is safe and that we are risking things properly. And geoscientists and engineers play a key point in that. So that's the societal there. A whirlwind tour of an overview. So let's go ahead and focus in on geoscience because that's kind of the focus of the talk here. And let's talk about regional specifically. And so when we use two views here to talk about the scale of a carbon storage project, we have an aerial view and we also have a cross-sectional view here on the right. And the storage site is broken down into several pieces. So this is where we typically think of all the action happening. The storage site, this is where we inject, this is when we see a profile of a well and a plume moving off of it, it's a storage site. But geoscientists know that things don't just stay in place when you inject them. It's subject to migration and movement in the subsurface, depending on the rock properties, the nature of the pressure, all sorts of different things that are happening in the subsurface. So in the cross-sectional view and in the aerial view here, we see this is a storage complex. So that includes that injection reservoir, also includes any secondary storage units like migration through into the cap rock, leakage that may happen in the cap rock, and most importantly, this overburden piece, because realistically, the number one goal of any CCS project primarily is, well, to protect the safety and health of people and society, but the drinking water is a massive part of that, and that lays in the overburden. So we're not just looking at the storage site here, we're looking at what's going to happen in the whole geological storage complex. And so I bring this up because knowing how far and what is going to happen to this plume once we inject is a primary piece of assessing a storage project. As geoscientists, we know, like just like petroleum or mineral exploration, we don't go in and drill initially. We assess the area, we do a regional risking assessment, and that's kind of like looking at the whole storage project. So we know the risks, we can budget properly, we can greenlight projects, we can leave ones behind that are too risky. So that's kind of the point of this slide, is to just set the context for the type of scale that we're actually dealing with and why are we modeling it the way that we are. And so this is a bit of a cheeky view of the types of data and where geoscientists add value in this space. So all the point of this is to say we use lots of data, and a lot of this data is data that we've touched and processed, modeled, and interpreted throughout our careers. And the data can similarly be used for CCS projects to kind of assess that whole carbon storage project. Being said, a lot is different. So what we like to say here is same skill set, new problem, same data, new problem. I don't like the word problem. There's a quote I read the other day that said, fall in love with the problem, not the solution. I like to kind of flip that and say, because geoscientists, we love challenges. We like to sink our teeth into something, really get into the issue, and try to look for a way to kind of get through it and kind of find some kind of an answer, or at least risk it. So I would say fall in love with the challenge and the solution, because I think we can move forward with being a key part in finding the solution for picking the best storage sites and moving things forward in an efficient way. So just to highlight a few of the differences with the carbon storage project modeling to, say, a petroleum exploration program or a mineral exploration program. First of all, the data. Saline aquifers typically have low data. So if we're focused on saline aquifers, we have to realize that these are often drilled through, drilled into, and abandoned. We don't collect a lot of data in these. So the availability, distribution, and quality of that kind of data is low. So we're dealing with rehashing data, getting new data, dealing with ways to work around low data. As we mentioned in a couple of slides ago, we're not just dealing with the reservoir here. We need to understand the entire storage complex, the seal, the overburden, the lateral extent of anything that we're looking at, how things vary, heterogeneity, all that kind of stuff. How the reservoir will respond if we inject into it, how risky the reservoir is in terms of faults and structures, thermochemical response, stress, things like that. How we go about planning our injections, and again, that caprock integrity. How are we going to keep the CO2 locked up, and what is the risk in terms of structure or heterogeneity or anything that's going to affect how the caprock can be integral to the system. This will help us develop our storage development plan, do risk assessment, and importantly, plan for our measuring, monitoring, and verification, which is going to help us ensure that everything is tickety-boo as we kind of proceed with our injection. And so this is really where we want to get to. This is a model here, a simulation model of the Schleipner CO2 storage project, which is located in Norway. It's the longest running, the North Sea, I should say. It's the longest running storage project in the world. And this is just showing you an injection well and then a CO2 plume that's been modeled over multiple decades. So what the need here is the best storage model that's going to consider capacity, injectivity, containment, monitoring, access, all that kind of stuff. And we use flow simulators to help us get an understanding of how the CO2 will kind of react. And these flow simulators are unique, and they need to take into consideration things that a classic reservoir model might not, such as really long-term spatial and temporal scales. We need to use the right flow physics to model that plume. We need to be able to consider the whole geology. We need to understand all the baffles and barriers, the heterogeneity, the rock property makeup, and how integral the whole system is, including the seal, not just the reservoir. And so just to kind of, and what I hope I've talked to you about in this section specifically is around needing really more efficient ways to complete our regional appraisals and site assessments. We need a lot of these projects. Like we've got that 100-time stat up there on purpose. So what we say here is we need to reduce the time to first storage. So with many projects, many things to evaluate, the best thing we can do is come up with the most efficient way to evaluate sites to move forward as quickly as possible. Greenlight certain projects, shelve other ones, and move forward with that. So in order to appraise those sufficiently, we really do need to take into consideration how the plume is going to move in the subsurface. This is no longer just an engineering of say, the way that we engineer with petroleum in terms of production. We need to be very efficient about understanding how the CO2 flow will move and how it's different from other fluids that we're moving in other traditional ways that we've done that. So the faster we can get to a good simulation model, the finished simulation model, the faster we can either move ahead with the project or shelve it. And that helps us get to where we want to be, which is actually executing on that. So in the next step, I'm going to go forward with forecasting CO2 storage. And in this section, we're going to talk about flow physics that govern the migration and trapping of CO2. And so again, we're focused on saline aquifers for this talk. And in saline aquifers, when you inject CO2 into them, they're considered a non-wetting phase, and they displace the saline water that's in the pore space. So we can think of this as a two-phase CO2 brine system, which is like a two-phase oil-water system fluid pair. And this generally means that they're immiscible, which means they generally don't mix. Whereas like in an EOR system, enhanced oil recovery, where you're injecting, or depleted field where you're injecting CO2 into it, it might mix, or it's miscible with the hydrocarbons. So it's a different way that we model, but in this case, they're two-phase. And so it's a lot like this oil and water analog here, it's actually very similar interfacial tension between an olive oil and simple tap water. So this is a good kind of analog for it. And what we want to do is once we've captured that CO2 and we're ready to, we're injecting it, it has to be in terms of phase, so this is a phase diagram, within a liquid or a dense supercritical phase. So that's a density of about 700 kilograms per meter cubed, so it's slightly less dense than water, but it maintains a viscosity of gas, which is kind of nice for flowing. The volume ratio stat I've heard on this is by compressing down to a density that's supercritical. It's like taking 356 soccer balls and compressing them into one soccer ball. So we're reducing the volume, we've got favorable flowing mechanisms, and that kind of critical depth is about 800 meters. So it's a great spot to take advantage of nice thick overburden. We're away from the aquifer. We've got diagenesis and cementation working for us. So it's a plus to have it in this supercritical state. And then once we've injected the CO2, the success of any geosequestration project lies in the efficient use of pore space for to keep that stuff locked up. And we need a thorough understanding of the transport and the trapping mechanisms while we inject. And so focusing specifically on trapping, we can trap via physical traps or by geochemical traps. And I'm highlighting the physical traps because for the majority of time since injection stopped, so we've got our trapping contribution and our time since injection stopped, it's going physical trapping, structural stratigraphic, the geometry of the trap, and any residual trapping that's happening due to sort of capillary forces are going to dominate. So if we don't nail this down, we're not getting enough contribution from our other trapping facilities. So I will just say that that this is just really important for us to nail, and there's some nice geology representations here, sort of images, which are nicely capture the different ways that we can trap CO2 within the pore space. And we're going to focus on how physics control how CO2 flows and migrates in the subsurface. So what does it do once we inject it, and how do we kind of understand how it moves? And which equations do we apply to model the flow? Those dictate which simulator type we're going to use. So this is one of the most significant challenges in understanding a CO2 project is using the right flow physics at what right time. So everything in our world is governed by physics. So we'll just do a really simple dive into the governing physics that kind of act on a fluid once you in any time and space. So this little happy guy is going to help me here. And we're going to start off with this fire hose. It's pumping water out. There's a pressure being exerted from the pump. So this is considered a viscous or a pressure-based force. So the water is exiting the fire hose. Once it exits the hose, it no longer has that pressure on it, and now it's subject to these gravity or buoyant forces. And that's due to the density differences between the water and the air. So it's kind of subject to the forces, and then once it hits the ground, it's subjected to still gravity, but capillary forces, which are dominantly these resistive forces of the pore space, and the water is attempting to percolate through, and the capillary forces are resisting that water. So we basically can say here that all three forces are always at work, but one will typically dominate over another. And as an example of that, like viscous forces in traditional reservoir and production conditions, as modeled by Darcy flow physics, those will dominate over gravity and capillary. However, when we're outside of that pressure, we have other forces acting on it, such as the balancing between gravity and capillary in the cases of, say, other buoyant fluids moving in the subsurface, like petroleum migration over geological timescales. So to talk a little bit more about that, let's take a look at this cross-section here, which pulls those force regimes onto a cross-section with an ejection well. And proximal to the well here again, if we're injecting CO2 into the subsurface, we know that we've got a pressure-based viscous kind of system here going on. So we're injecting in at this well, but as we move away from that injection force, we start to move into a hydrostatic pressure regime. And this is where gravity and dominated physics are going to take over. And really, this is where the plume is going to spend most of its life. So if we need to do a first pass regional assessment, we really need to understand what's happening out here, because this is only going to be relevant for so long. So understanding how the CO2 is going to move away from the wellbore and what happens to it once you stop injecting is really important. And so how we model that typically is we use what's known as invasion percolation modeling. And so I mentioned Darcy flow physics here. This is the viscous-based forces, whereas invasion percolation is what we use to capture the capillary-dominated and gravity-dominated flow. So it kind of like models both of those at the same time. And this is a non-Darcy flow algorithm. And so it's been used for years. We've used modified invasion percolation for years to model multi-flow physics or multi-phase flow problems such as migrating petroleum. And it's worked really well. And really, this is another way that we can model another type of buoyant fluids moving in hydrostatic pressures, such as our CO2. Figure out if we're in this regime is we can calculate a capillary number, and this is a unitless number that basically takes the viscosity of the most viscous fluid of the two that you're modeling, the flow rate and the interfacial tension, and we calculate a number, and if it's less than 10 e to the minus 4, then we're in a capillary dominated regime. And so to give you an example of that, the Schleipner project, again, just bringing that up, that's about 100 meters is where we drop into capillary flow, and that we know that from comparing monitoring data to invasion percolation modeling. Good matchup. So we're confident that that far away, we start to move into this kind of flow regime, and we can use invasion percolation flow physics to model that. So you might ask yourself, well, why does this matter? Well, if we don't get the right type of simulator at the beginning of the project, it's going to be hard for us to do a rapid appraisal because invasion percolation flow physics are much faster to run than Darcy flow physics as well. So we'll talk a little bit more about all of that, but just to say that there's no right answer, there's no right simulator, but we really do need to understand the when and where in order to apply the right flow physics. I'm going to attempt this video because sometimes videos in PowerPoint are funny. So if it's funny, I have the actual raw file loaded as well. But just to talk about why capillary forces are really important to understand is because it also helps keep our CO2 locked up. So this is a little video from Philip Ringrose. If you want to go to his YouTube channel and check it out. But basically what he's doing here is he's using a simple aquarium to show capillary forces at work to keep locked up. So here he's got a little experiment. I got some bookmarks here to help us along, where he's got a food sieve representing a trap, and all he's doing here is pumping air in and saying this is basically our CO2. So the CO2 is building up underneath this trap, and the food sieve has specific capillary forces and within the sieve that are higher than the buoyant pressure from the fluid that's coming in. So as long as we don't exceed that, everything's going to stay locked up. Whereas if we do choose to exceed that, so we increase the gas volume beyond that threshold pressure, what we're going to do here is, one moment here, you're going to see a leak off here, and the whole thing is going to let off enough gas that the maximum volume, we just have this little residual volume here. So this is helpful for us to know also for injection rates and understand the capillary threshold pressure CO2 locked up, and how important it is for us to understand the heterogeneity of this seal. What if we have higher threshold pressures due to some kind of heterogeneity? I encourage you to kind of go check that out if you, if you get a chance here. Just go back into full screen. So show you what that looks like as a cartoon. Again, the petroleum or the buoyant fluid is trying to get through this brine, and there's a pressure differential between the buoyancy and the resistive forces of the pore space, and that's that capillary or resistive force. So really we're trying to capture the effect of the two together, and whether the pressure differential will decide whether that moves on to a new pore space or whether it stays locked up. Petroleum system modelers on the phone, this should be super familiar to you because we know how low threshold pressures in a cap rock can allow, this is in this case petroleum, enter a trap, and then it sort of backfills to capacity, and then it overcomes the overlying threshold pressure. So capillary trapping is super interesting and important to understand. And another point to make on that kind of building on the capillary trapping, heterogeneity and the threshold pressure differences within a unit that has a fair amount of heterogeneity is a major influence on capillary dominated flows, and it affects how the CO2 is going to move and where it's going to migrate and what the shape is. And to show you what that looks like with sandbox models, two things we love as geologists: we love aquariums and sandbox models. So both this presentation has both. And in this particular model here, we're showing a very basic homogeneous medium. It's a sandstone that basically has no heterogeneity in it, and we're subjecting it to a strong fluid flow, and we can see that the shape of the plume here and the extent. Whereas if we did not have to get rid of that heterogeneity, or we understood the heterogeneity due to, say, better data or better modeling, the shape and size of this plume is completely different. So it increases the efficiency of our pore space utilization, and we can help understand how the CO2 will actually behave in the subsurface. This is really interesting and important for understanding risk and leakage. And just to show you how well invasion percolation models that, so we can ingest this kind of a model, and we can really match up our sandbox, these timestamps to Permedia. Now, I will say that our Permedia CO2 simulator, this probably would take about less than a minute to run. So these timestamps actually just represent the fluid kind of slowly moving through this rather than the actual run times. But we see very good collaboration or matchup between the simulated model and the sandbox model. And so I would say here, just kind of sum up the invasion percolation section, is that there's many benefits to using a different type of simulator than a traditional reservoir simulator, which many folks are used to using for CO2 and for production. Darcy flow physics for regional assessments have a number of challenges. We have a hard time holding up the actual scale and heterogeneity with reasonable run times on models. So nobody wants to wait 8, 10, 12 hours to run a model, or 2 days, 3 days sometimes for a very complex model. It means that you may have to upscale your model to remove some of the details so it runs faster. And that's really difficult if you want to run several models with several different scenarios. Understanding how that CO2 is going to move outside of Darcy flow or Darcy's law, Darcy flow physics. We have good collaboration, good studies, good benchmarking saying that IP works really well in low moving heterogeneous environments. So it's another tool in our toolbox. And as well, it's good for us to be able to get a good seal integrity analysis because we can model that capillary dominated force really well. So those are just kind of some good points about using invasion percolation or modified invasion percolation as a simulator for our kind of long-term post-injection modeling. Just moving on to kind of, okay, well, now what? So if we want to use it, what are our options? Well, for us at Landmark, Halliburton Landmark, we have a piece of software called Permedia CO2, and this is developed with support of industry and academic organizations as a result of a consortium. Many years ago, this group was pioneering CO2 storage. They were looking at existing commercial simulators, and they were saying, hey, we model buoyant fluids, hydrocarbons, using slow-moving fluids using migration simulators over geological timescales for traditional petroleum system models. Can we adapt that for CO2? And so what they ended up doing was putting together this toolkit, which is literally a set of tools with different simulators. So we do have a Darcy flow simulator, but the real crown jewel is our migration simulator, which uses invasion percolation to model CO2 migration. And what that does is it gives us a number of integrated tools so that we can do assessments for anything from basic 2D prospecting all the way down to injection scenarios and solubility with our black oil simulator. And we can look at that also, that long-term fate using the invasion percolation. So another thing I always point out to people is if we understand if we are leveraging an existing framework, it's great for us being able to use tools that already exist, that we already use as geoscientists. So Permedia as a petroleum system modeling tool already had great data interoperability with over 100 data formats, ability to bring in your own scripts, your own algorithms, your extensions. You can couple it with other simulators. So basically, we're able to leverage all that stuff and just use the CO2 adapted work that's been done on the platform. So it's been really helpful in that space. And don't take my word for it. We have a number of publications over the last couple of decades, and most importantly, we won a World Petroleum Council Award for technology development in excellence, and this is all based on an article that was written by Florence Bebb earlier last year. And so I'm happy to put that link in the chat. It kind of summarizes what I'm saying in a much more eloquent manner on the flow physics and how this is kind of important for long-term storage modeling. And so I'm just keeping my eye on the time. So Callie-Ann, feel free to cut me off, but I've got about a 6-minute little video demonstration here. And so this is going to take us through 2 short workflows. Again, we have a lot of different simulators we could show you, but today I'm just going to show you what's it like if you want to do some quick RAP screening. You have a map, you have a basic understanding of your reservoir, and you want to play around with some injection points, take you through that workflow. And then the second part is, okay, we've chosen a site, we want to go into 3D, we want to do a little bit of flow simulation. I'll just show you what that looks like in our flow simulator. So what I'm going to do here is I'm going to use a video to show you this. I would love to demo this live, but I've actually purposely chosen a video because I will talk for probably 30 minutes if you give me a chance on this or more. So having a video that's less than 7 minutes is going to keep me in track. So it's your lucky day. But if anybody wants to see this live, I'm happy to do it for you. Head and start this off here, and I'm just going to talk over this video. So starting off with these map-based prospecting tools, this is going to help us rank our injection sites. So this is the Permedia map viewer here, and all we have loaded here is a CapRoff map. It's a simplified version of, again, that Schleipner model. And under our workflows, we have a bunch of different rapid screening tools. And these rapid screening tools can be used to basically assess closure fetch areas for the hydrodynamic movement of any buoyant fluid. We can do trap volume analysis and understand kind of like pore space volumes. And then we can also do what I'm about to show you, which is fill spill analysis. And this is basically where we are going to go about choosing an injection point. So I'm just going to click here on the map, and you'll see an injection point, which is then populated within this list. So I could load in a well, or I could click on the map. And what we're outputting here is a accumulation state of that fluid. So, as well as you can see on the left, there's a map basically of what you're looking at. So you could use it in Permedia, or you can take it out. And what you're seeing here is the green is representing that plume. The red is representing the migration pathway. If there were any spill points, like it was spilling to another structure, then we would see those in yellow. So it's important to point out here that this is not a purely geometric, but it's dynamic. So it's taking into account the buoyancy of the fluid, the seal, the structure in how it models. So basically what we can do here is we can insert one or more points and just kind of click around, and it's really easy to get an idea of that. And then here, basically what I'm showing you is I've just changed the output here to sequence, and so we can also look at the filling sequence, and in this case there's been a number of points that have been added, so maybe we've loaded in some potential well locations, and this just gives us an idea of how this giant structure continues to be filled, but also we're taking advantage of some of these smaller structures in here. And then also, there's a number of options under the Properties tab here, which if you did have information about your reservoir, threshold pressures, you wanted to add some baffles and barriers, you can do that. But if you have, one of the big things is you might not know the actual depth of your map too well, so you want to add a plus or minus uncertainty. So here we've added 5 here. Now we're going to run 100 sequences, and we're going to see what those realizations look like. So when I go ahead and run that, I get a kind of a quasi CCS map, traffic light map. Green is where we have CO2 appearing in every one of our outputs, and red is basically where it's in very few. So we get a pretty good handle on the uncertainty of that trap based on running a number of realizations with our depth uncertainty. And that is basically one of 3 map-based workflows that we have. And what we would say here now is once we've kind of done our map-based prospecting, now I'd say, well, I want to have a hard look at that big structure because it has the best capacity and I like my injection site. So let's go ahead and do some more integrated migration modeling. So in this next part of the demonstration, we are going to move into that in-depth. we're going to look at now is our migration simulator. And so that's going to simulate the emplacement of the plume distributions over time, the physical and pressure-related trapping mechanisms. And again, we're using modified invasion percolation techniques to mimic that interplay between the buoyancy and the capillary forces away from the wellbore and away from the injection site. So what we're looking at here is a very simplified version, very simple, sand, shale, different properties on the shales, but you see a number of very thin and thick interbeds. And so the input mesh here, it has a number of rock properties on it. I could have built an earth model and brought this in from another software and just read it into Prometheus, or I can use Prometheus solvers to go ahead and generate these rock properties here. We also require a full pressure and temperature model in order to run this. And so basically, in order to do that, we take that mesh, we load it into this wizard, and it's really straightforward to use. Take it from me, I'm not an engineer, so I love wizards. I like to be walked through the steps, and that's exactly what we're doing here. We've got basically a set of tabs that we're going to work with from left to right. And we're going to start with the source tab, which is where we're going to load in our source points. Those could be well injection points. I could physically click on the model and generate them. Doing here is we're defining our injection points as either constant masses, like I'm injecting here and I'm injecting this much, or via an expulsion file, which is the way that we can define an actual injection schedule. And then next in the sources tab, this is where we take those rock properties on the mesh and we handshake them with the most important rock properties. We also need to define our PVT settings. So that's our density, our interfacial tension scale, our pressure, our temperatures, and then this is really important for us to define our pressures and temperatures. We can also run single phase or multi-phase. Multi-phase, this is where we can take advantage of our PVT kind of tailor-made user interface for media. So when we pop that open from the migration GUI, it looks like this, and it's essentially an interface for storage modeling, and it's an PVT IFT equation of state wizard. So we use that to generate the kind of PVT data that we need for those multi-flow simulations. We can populate our initial storage models, we can define our brine density, compressibility, viscosity, solubility, interfacial tension, and basically we can play around with this. We're able to visualize that, and we can pop that back into the model once we have completed running that. So all I did there was kind of fast, but I hit the run button and it just popped it back in, and it populated the simulation tab with the right PVT information. We can do that for any of our simulators. It talks to the black oil simulator, it talks to all that kind of stuff. So we can go ahead and run this, and that was literally one click, but I've run this model several times. It takes between 15 and 30 seconds to run with our simple model. Now we're then looking at the simulation in 3D. And one of the noteworthy characteristics you're going to see here is that this plume was injected down here and it's sort of migrated through. And you're going to see that the layers, these kind of shaly layers, have kind of formed interformational barriers that are kind of setting the scene for how that plume is going to be modeled. And we can see kind of how things have backfilled and taken advantage of those structures, and how there's like these residual kind of trails that are following it. And then if we switch that property to threshold pressure, we can see the impact of the lower threshold pressures in the sands, the higher threshold pressures within those shales. And what we see is this plume kind of beneath this cap rock here. And we've gotten those threshold pressure values from some laboratory tests that we can kind of compare those with. And we can also consider how microfracturing, when the study was done, there was a lot of pore pressure changes during the last glaciation that happened in this area. So we're able to incorporate those in and understand how those would affect pathways of the CO2 underneath of this cap rock. And then we can also look at the plumes in 2D, which is nice to kind of look at the structure, how this is being filled, what's the capacity, and we can use a lot of the post-processing tools to then look at the actual properties per accumulation. And that's really how we dig into the results of the viewer. And then I'll just end this little demo by showing you an animation. That's the same plume in 2D, but we're looking at it as a point cloud. What we can see here is the pore saturation levels. And we've done an injection schedule so that we can kind of we can timestamp this and we can animate this and walk through it. So here we're going to play this animation and show this concept. We see the plume migrating, we see it backfilling, we see it breaching the threshold pressure, the seal over top of it, the interformational seal, continuing to backfill the next structure, and then escape and migrate up to the next one. So pretty important for us to be able to incorporate the heterogeneity of this particular reservoir and understand the impact of the plume. And we see good collaboration or calibration between this and the monitoring data from 4D seismic in the Schleipner area. So that is a little sneak peek of Promedia and how it kind of works. And what I will do now is just go back to my presentation. I'm just keeping an eye on time here, and we've done a number of kind of benchmarking studies using Promedia, and what we've been showing you is the Schleipner model, which is really well understood. I don't really have time to go into detail, but we have benchmarking studies in Weyburn up in Saskatchewan in Canada by looking at legacy well mitigation risk and CO2 containment using a lot of our migration and map-based viewers. We also have done work in the Insala area looking at the fractures and the fault impact there. So highly encourage you to you're interested in legacy well impact in particular, which is a real challenge in North America. If you Google Kavanagh and Weyburn, you'll get a number of his studies and presentations, and as well as Schleipner. So just backing up and concluding the talk for today, I just wanted to conclude by ending with you guys, ending and saying that geoscientists, we believe that geoscientists and CCS play an important role in our net zero goals for 2050. We can bring our knowledge, our workflows together. We can adapt to the challenge of assessing storage sites in a quick and efficient way. Simulation is going to be a very important part for assessing, in particular, saline aquifers for high potential capacity for global CO2 storage. We need to have this done during the pre-permitting appraisal and during the post-permitting operation. We play a role throughout the whole life cycle, and simulation and getting that part right earlier on and quickly is really important for us to kind of efficiently move forward with the best projects. So this is a real economic driver as well for simulation. Like, we want this to be successful. We want society to do well and companies to do well off of this, and we don't want to waste money. We want to be as efficient as possible. So we need to use the best physics, the best tools we have. And so this presentation was just giving you another tool to assess and another way of thinking about flow physics outside of what we've thought of traditionally for CCS. And so with that, I will conclude and I will stop sharing my screen. And if folks have questions or want to reach out to me directly, I can put my contact info inside of the chat box. Okay.
Hey, Kate, it was an interesting one. Thank you very much. Interesting presentation, and we ended up right on time. And we have got about 8 to 10 minutes for some of the Q&A. And yeah, so there are a few questions which has been posted in the chat as well as in the question box. Okay, yeah. So again, in general, this session is being recorded, so you will be posted it in our EAGE website, and then probably you'll find there a link of this presentation. Okay. Let's go to some of those questions. I think Jeffrey has asked, first question is as the pressure drops during flow, what is the risk that the super criticality of the CO2 will be lost?
Yeah, that's a good question. I think getting the initial, I think you need to understand the pressure of your reservoir first. When I say pressure, I mean induced pressure from the injection, but the storage site itself will have its own pressure values. So if it's under pressure, what you're talking about is a risk. So you would use that as part of your initial injection, initial storage evaluation, the temperature and the pressure, and your PVT information, just to ensure that it everything is staying in the phase that you want it to be in post-injection. So that's my non-engineer way of thinking of it is, we ensure we get the pressure and temperature right. And then when we model it, we should be able to tell if it's not sufficient. That's how I would think of it.
So basically, during the modeling process, you will take care of that super criticality issue, probably.
Mm-hmm.
Yeah.
Yes. Yeah. That would be
Okay.
part of it. Yeah. So
Next
you use a
question.
wellbore.
Oh, go ahead. Sorry.
Sorry. So a couple of simulators I didn't talk about, like a Wellbore Simulator, which is what you're using for, the surface to near reservoir as well. They have their own ways of ensuring that down the wellbore we're staying in the right phase and all that kind of stuff too. So those are specific simulators for like inside the wellbore as well. Yep. Okay. Sorry.
Okay. So next question, the flow simulator, does it honor the fault or the fractures?
Yeah. So the key to that is modeling those up front. So first of all, the juxtaposition of different units against each other, getting that right in the model structurally, and then as well, like things like shell gouge ratio and the rock property changes, whether a fault is transmissive or it's sealing, we would incorporate those via the rock properties into the mesh. So the 3D geocellular model would need to capture that. So we can do like local grid refinement along a fault and then define the rock properties of that fault, and then make sure that's part of the input mesh for the actual simulation.
Okay.
Yep.
So while we're going to the other questions, can you post the link of that paper you mentioned?
Yes, I will post that right now. So this is just it's a pretty short article done by one of our technical advisors, and it's just available from Halliburton. So I'm going to throw it on the chat.
Sure.
Sure. And
okay.
So I'm just going to put in the questions here, I think.
Okay. Yeah.
I hope that works. You might need to click through something, but yeah.
Yeah. Okay. We can see it. Okay.
Okay.
So yeah, let's go to the next question. Like it's from Yanni. Like is the flow simulator considered fault and fracture? Oh, you have already covered it. So the flow simulator, whether it takes care of the fault and fractures. Okay.
Yeah.
Okay, we'll go to the next one. Basically, it's related to the tool for the Parmedia toolkit. Actually, what are the information is required to run it?
Yeah. So the simulator itself requires a mesh. So it requires a 3D geocellular model that has properties, and I think have to bring open the list again, but the property list is threshold pressure, has to have water saturation, porosity, permeability in both directions. It has to have threshold pressures, as I said, and I think that's it. So what we typically do is, if you're doing traditional reservoir modeling, like earth modeling, static reservoir modeling, you can calculate that. But what's nice about Parmedia is there is ways to handshake rock properties. So maybe you only have a porosity volume from seismic and you don't have time to do a full earth model. You can use our rock property files to kind of handshake porosity with permeability, with threshold pressures, depending on what lithology you've chosen to represent that interval. So it's a way of kind of back populating those until you have better data from core or from something else. And we do leverage seismic volumes as well. So like if you needed to use a seismic volume and again, make that transition to a property model with all the properties that you need, you can do that. So that's another way that you can kind of leverage other data sets. So.
Okay. Yeah, so that means traditional modeling output from the earth modeling can be directly used in this toolkit. Yeah.
Yes. Yeah.
Okay, there is another question which is a little bit about the consortium you mentioned. So can you talk more about who are the members of that consortium?
Yeah. So the consortium is like it was how Parmedia was formed, and then around I think 2012 it was purchased. The whole software group was purchased by Halliburton. So consortium is no longer like the software is no longer like defined by the consortium, but I always mention it because I like to think of, again, the collaborative nature of all these industry and and academic folks getting together. And many of them we still support through academic grants and things like that at U of T, the Gulf Coast Carbon Center, folks like that. But the original consortium members, I'm just seeing if I've got the list here, but it was BP, it was Equinor, again, it was the BEG group, and a bunch of other, I'm just looking for the list here. I took the list off because I didn't want the logos on my slides because it's, you know, we're now part of Halliburton, but I can send the list, but it's actually on I think it's on our website as well. But yeah, it's several big companies, and Equinor was a big part of that because of the Schleipner project, and Philip Ringrose's involvement with publishing some of the efforts from that. So yeah. So sorry, that doesn't answer your question completely, but.
No, I think that's okay. Probably, you know, you have provided that information about the website, and then okay. So let's go to our last question, and which is probably related to some input what you have provided during your demo, because the question says, is your leakage of 0.1% per annum for 100 years or for 100 years? The question is, is the leakage of 1%, 0.1% per annum, or for 100,000 years?
Yes, because I said 1,000 years at 0.1%. That is a great question, and I actually don't know the answer to that. I know Sheila's on this call. Sheila, do you know the answer to that? Because I pulled that quickly off that report, and actually I didn't think about whether that's per year or per 1,000 years. I feel like it's per year, but Sheila, if you can unmute yourself and you.
Yeah, I just added Sheila to that, you know, into the presenter. I tried to edit her, but hopefully she'll be able to.
Yeah. If not, I can just look at the reference.
She's there.
Really. Yeah. Oh,
hey,
perfect.
Sheila.
Hi, Sheila.
Hello, sorry.
Hi.
My apologies, I had a few problems joining. I'm actually at the EAGE CCUS, so competing scenario for you all, and I apologize for the background noise. My little quiet spot has got noisier. So the background to this is that when we started looking at CO2 leakage rates, 1,000 years, making sure that, you know, CO2 is going to stay in the ground for 1,000 years. So that's really where the 1,000-year concept comes from. Now, 100 years gets bandied around because, you know, as I always used to say, you can't keep a gas down. But the 0.1% comes from basically that's the minimum acceptable leakage rate. And normally, if you're saying California, the regulatory system there will say that they want to have 99% of your probability of your leakage scenarios are less than 0.1% leakage rate, or so some range there. So there are different ways of looking at it, whether it's a temporal scale that CO2 is going to stay there for a number of years, but then a specific leakage rate that you gain from your probability scenarios from your modeling.
Okay, that makes sense. Thank you, Shelagh, for connecting to the call and then able to answer the question. Kat, if you want to share anything else, because, you know, we have ended, that was the last question. Let me check again one more time if there is anything left. No, you have already sent a paper link. Yeah. So that's the last question I had. I received. But if you want to add any other thing to your presentation, yeah, feel free.
Yeah, no, I just thank everybody for their interest, and yeah, feel free. I'm just going to put my email in the chat here, and you know, I appreciate everybody coming out to kind of learn a little bit more about options and different ways that we can kind of tackle this problem. And I would say there's the other thing is, if anyone's kind of new to this and they're looking for like a really decent overview, I know I've referenced the heck out of them in this presentation, but Philip Ringrose has a paper, or sorry, many papers, but a book called How to Store CO2. It's a 2020 publication, and it's a great overview of the whole life cycle process, and it's going to give you a really good kind of understanding of how everything works. So that's a good reference if you're looking for that. And I'm just going to put my email in the chat here, and also a data sheet if you want to like understand a little bit more about Permedia. I mean, I'm not trying to sell anything, but just to give folks options. So you know, feel free to reach out. And yeah, thanks again for your time. I don't know, Shelagh, did you have anything else you wanted to add?
No, I mean, unfortunately, I had to miss the first part of the presentation because I had some issues logging in. But, you know, as Kat's probably mentioned, this is so much a simulation problem. You know, it's from a geologist's point of view, it's great. I've been doing this for 20 years now. It is a geoscience problem and it's a simulation problem, particularly when we start looking at these large capacity saline aquifers. And so I think what Kat's been showing is it's very much how can we speed up the process of really understanding the subsurface and how we can really try and de-risk the whole process. And this is why this sort of work and this approach is in our view so important.
Thank you. Thank you everyone for joining the call, and I apologize for the little bit of technical hiccups in the beginning to join the call, and we'll try to minimize that for our next meeting, and we'll try to provide that link. maybe that was one of the main issue, like finding out the link how to join this call. We'll try to rectify it in our next meeting. Thank you again. Thank you, Kat. Thank you, Shelagh, for presenting.
Thank you, Kelly.
Thank you.
Bye-bye.
Bye.